chat window where you're dialing in from. I'd very much appreciate it. We're just doing some big data analytics on all the data we are getting and figuring out where people are dialing in so that we can figure out. I'm just kidding. So I think there's someone from Paris, New York City. Hi, John. Brookline, Massachusetts. Toronto. Austin, Sibley, Atlanta. So I think we have most of the United States covered, at least many of the New England states, at least, and from Nigeria. So thanks all of you for joining in. I think we have gone live. So welcome to the QuantUniversity Winter School 2021. This is the 5th session in the series of guest lectures we've been having since January. And the theme of this year has been adopting machine learning in production and many of the issues associated with adopting machine learning. And as you all know, in the last year or so, there has been significant developments in the area of explainability and interpretability in machine learning models, as you bring all the important aspects of machine learning models into production. With the sophistication of models, with deep learning, with black boxes, there's been a lot of interest in trying to understand how you can not only get to interpret the results, but also kind of go under the hood and figure out what these models are actually doing. And as a part of the research, when I was kind of looking at various research efforts, I came across Marco and Nadia's amazing paper focusing on explainability in the context of supervised machine learning. And as you all know, we have had many lectures in the context of explainability and interpretability. Last week, Dr. Anupam Datta from Carnegie Mellon University presented their work and the work they do at Truera. And we have also had many lectures from practitioners like Agus gave an amazing presentation last in the fall school. And also Patrick Hall gave a presentation on machine learning and explainability and key aspects of algorithmic auditing, etc. a few weeks ago. So our goal is to try and democratize this notion of research and also making it available in a consumable way for practitioners so that we practitioners, when we kind of apply these methodologies, we have a holistic perspective of what are all the things which are happening in the world and how we can adopt them in a practical sense, and also to foster research to build upon the various ideas which has been researched and thought about throughout the world. So I'm so glad that you're all able to join us today. And the slides for today's presentation will be made available to all the registered participants by email later. So I'm just going to do a couple of quick announcements on some of the things we have been doing here at QuantUniversity. And for people who are joining in for the first time, welcome to the QuantUniversity Winter School. I'm going to do a quick introduction. So we're based out of Boston, Massachusetts. And we've been working on various aspects of the intersection of data science, machine learning, and finance for the past close to 8 years now. We have done educational programs, do a lot of advisory-related work. We're also building a platform called the Q Sandbox to basically make all these tools available in a pragmatic way for practitioners. In addition to that, we were fortunate to basically make the QuantUniversity Winter School and the Fall School available to all the participants. One second, I can see how I can, just a second. See if I can make it into a bigger window. And we are also gearing up for the Spring School 2021 starting April. And during the Spring School, we plan to extend the discussions of various things happening. And we are fortunate to partner with Premier, and we are offering 6 courses. The first 3 courses are primarily geared towards practitioners who want to kind of enhance their knowledge of machine learning and data science and focus on model risk management. And we have also been tracking some of the innovations which are happening in the fintech world, and we are building a course. And that's a course I actually teach at Northeastern University in the business school. And we have two new programs, one on algorithmic auditing, and we are focusing on pragmatic ways in which you can operationalize algorithmic auditing, primarily for machine learning and AI models. And the second course is called risk and machine learning models, stress testing, scenario testing, and evaluation, where you'll focus on the practical methodologies on how you can stress test machine learning models. In fact, all these three courses are available for Premium members at a discount. So if you go to prmia.org and go into the courses section, you'll be able to register to any of these courses. The first three courses are all available on demand, and the rest of the courses will be made available on a weekly basis starting April 1st. So I hope you can join us for the spring school too. Without further ado, I would like to introduce our eminent guest speakers today. So we're so fortunate to have Nadia Burkart and Dr. Marco Huber from the University of Stuttgart and Fraunhofer join us today in today's presentation. So as most of you know, the area of explainability in supervised machine learning is becoming an interesting and a topic which is very near and dear to my heart. When I teach machine learning to my students at Northeastern and at QuantUniversity, many times we have to not only understand how these models are built, but also how will these models be used? Are we just going to be focusing on accuracy, or are we going to be looking at different metrics? What are the different use cases, and what are the various domains and the concerns associated with each one of these domains? And especially when you're looking at both black box and white box models, how do you think about data? How do you think about models? How do you think about simplifying them? And what are the various metrics you could potentially use to understand? And they did a wonderful survey, and the paper is available on the site, and we'll also make the paper link available. And you should be able to get a lot of it just by reading this one paper, and it's a great place to start. And to introduce our speakers, Nadia received her bachelor's and master's from the University of Applied Science at Karlsruhe. And she has been leading various projects in explainable machine learning in various domains, and she's working on her PhD. And Dr. Marco Huber received his PhD from the KIT Germany. And he has done some, I was kind of looking at some of your papers, Marco, some really amazing work. And he has been leading various research efforts where he's, until 2018, he was a full-time professor at the University of Stuttgart. And he has also led various research efforts in machine learning, decision-making, computer vision, and robotics. So without further ado, I will hand over the stage to you, Marco, and we're allowed to hear your thoughts.
All right, thank you. So you should now be able to see my slides.
Yes, I can see it. Yep.
Okay, great. So thanks for having us here. So we give a wrap up of the survey we did recently, which is now published as the Journal of Artificial Intelligence Research. So the link this will be made available afterwards. To give you a motivation why it is a good idea to think about explainability, here I have a nice example. Consider a situation that you would like to build a classifier that is able to discriminate wolves from huskies. For instance, you have some images, some pictures. In this case, there's one of these animals. You build a machine learning model, and then, of course, you can guess by yourself, what do we see here? Is this a wolf? Is this a husky? And after some thinking, you might come up, well, this is a wolf. I give you another example, different picture, different animal. In this case, what do you think? I guess you get it. This is a husky. So I guess for everybody of us, this is a right easy task to learn such kind of a machine learning model, and then we apply it on labeled data. This was actually an experiment that was done some years ago.
Excuse me, Marco. By any chance, could you keep the microphone a little closer? Just to. Yeah. Thank you.
Okay. Is it better now?
It's a little bit better. Yeah. Thanks.
Okay. Otherwise, I'll try to speak a bit louder.
Please.
here you see some of these images, the predicted by the machine learning model and the ground truths below, and you can see in most of the cases the machine learning model behaves quite well. There's just one exception. There's one image which is classified wrongly, which seems to be not that bad. But if you look a bit deeper, you will see that there is some bias in the data. You have always images where wolf is shown together with snow in the background and huskies shown with a background without snow. So this you can find out with some of existing explainability approaches, like in this case it was Lime that was applied. And you can see that this machine learning model is actually not looking at any feature of the animal. It is using background information to make the classification. So in this case, you actually built a snow classifier and not a wolf husky classifier. This might look a bit, yeah, as a fun game, but actually this can become quite serious. Here, this is a analytics done by a software or for a software which is called Compass, which is a crime investigation or crime risk assessment tool, which is actually used in the United States, in some states, to assess the risk of recidivism of some people. Here we have some example. For instance, in the case of Vernon Prater, the software is giving a low risk of recidivism. And on the opposite, for Brishna Borden, the risk is quite high. The maximum risk, by the way, is a number of 10. But actually, then later out, it turned out that Vernon Prater did a grand theft, while Brisha never recidivated in the future. We have another example. For instance, for Dylan Fudgett, the software predicted a low risk of 3, while it was predicting the maximum risk of 10 for Vernon Parker. But later turned out that Dylan Fudgett was assessed for 3-time drugs possession, while Vernon never recidivated in the future. By an in-depth investigation of this software, it turned out, and this was done by ProPublica in 2016, that there was a very strong bias. So this software is using machine learning models, but nobody actually knows what they are actually doing. And it turned out that for the black defendants, there was a nearly twice as high risk to be classified wrongly compared to the white people. And also the opposite mistake was done for white people. So this software actually was discriminating people of color. And such failures, like in Compass, but also with our wolf and husky classifier, can be detected by using explainability approaches. So what is actually our challenge we have to solve? We know that we have quite powerful AI systems like deep neural networks or random forests, but these machine learning models are typically quite opaque. They are not intuitive and very difficult to understand, even for the experts, even though they can provide high accuracy predictions. From a user's perspective, you might ask yourself, why did a certain model do a specific prediction? Why did it predict something else? Why was it successful, or why did it fail? These kind of questions that might arise. And the topic of explainability or explainable AI is to give some answers to these questions in order to give a deeper understanding of the topic, to increase trust and allow to manage the output of AI systems. Now I would like to hand over to Nadia.
All right, thank you. So why do we need explainable artificial intelligence? Trust has several properties like fairness, responsibility, auditability, or accuracy. But explainability is one of the key enablers to trust AI. In Europe, we have the ethic guidelines for trustworthy AI that is prepared by the high-level expert group on artificial intelligence. The general objective of this group is to support the implementation of the European initiative on AI. This is an independent expert group that works on different guidelines, like for explainability, accountability, and fairness. All right. Okay, let us have a look in XI and public perception. So the research in the field of interpretable and explainable machine learning is currently exploding. And as we see, there was a huge exploding in since year 2015. Also, several newspapers addressed the topic of this topic, for example, in the Forbes magazine. Also, explainability was mentioned in the Gartner hype cycle. Actually, it is between the stages innovation trigger and peak of inflated exceptions. The time required to get to the plateau of productivity is 5 to 10 years. All right. So next slide. Yeah, in contrast of doing just only technical evaluation between the different algorithms, there are also works that examine the qualitative analysis of machine learning models. The main findings were there that the visualization, for example, of the feature importance was pretty helpful for the users. The non-experts preferred more simpler explanations that only explained a specific decision. Experts prefer to understand the entire model. And among all, short explanations with all information were pretty preferred by them. All right. Okay, so let us have a look at the Xi taxonomy. There are on hoc approaches that are either interpretable by nature or interpretable by design. We will discuss them in detail later. The ad hoc approaches are always specific. The post hoc approaches can use a surrogate, or explanations can be directly inferred. The explanations can be either local, that means they are for a specific instance, or they can be global, that means they try to explain the entire model. Also, the explanations are sometimes called static or dynamic. Okay, so now let us see 5 types of Xi. So the starting point is supervised machine learning. Yeah, so the first type we will explain are post hoc model explanations. The second type are interpretable models. The third type are global surrogate models. The fourth type are instance explanation. And last but not least are the local surrogate models. Okay, so let us go ahead to, first we'll have a short look at the problem statement of supervised machine learning. So yeah, of course, we have the data, and also we have the model that is parameterized by theta. So most famous examples are, for example, linear predictors that are concerned to be white boxes. And on the other hand, we have, for example, neural networks that are considered to be black boxes. So the estimation of theta is an optimization problem where we, for example, try to minimize the error on the training data. And the resulting model can be, as I said, either a black box or a white box. Okay, let's go to the first type, post hoc explanation. But before that, we will have some running examples on the IRIS data set. I think the IRIS data set doesn't really need an introduction, but for those who not know it, it's a multivariate data set. It is for the task of supervised machine learning. It contains 50 samples of 3 species. The class labels are Iris versicolor, Setosa virginica, and it contains 4 attributes. Okay. All right. So what are the common approaches? In our paper, you will find an overview for each of the explanation approaches. So for example, we have partial dependence plots. They illustrate a marginal effect on 1 or 2 features that they have on a predicted outcome. And they show whether the relationship between the target and the feature is complex or monotonic or linear. On the other hand, another approach is random forest feature importance. There we measure the importance of a certain feature by calculating the increase in the model's prediction error after permitting the feature. So the feature is important if the shuffling of its features increases the model error. Okay, so let us see some examples. So as I said, or as the name says, PDPs are presented as plots in which we either plot a classification against its partial dependence on one feature that is shown on the left side, or two features against each other with a map plot, as you can see in the middle. PDPs show the correlation of a feature it has to the classification of a certain class. In this type, or in this example, it is Virginica. Yeah, so the map plot illustrates the Virginica probability and the interaction of the petal width and the petal length. The plot shows the increase in Virginica probability if the petal length is greater than 3 centimeters and the petal width is greater than 1.8 centimeter. Another approach in this category is the global feature importance, as I already introduced. We can see on the right side. The global feature importance returns a list assigning an importance score to each feature. Together, or if you sum it up, it will be 1. This importance tells the user what features exactly are considered the most by the model. So this is a pretty first good entry for the explainability, but also you can combine it with other approaches. Yes, all right. Okay, so let us go ahead to the second type, the interpretable models. So this can be distinguished between interpretable by nature or interpretable by design. On the left side, you see the interpretable by nature approaches. So thereby the learning algorithms is not explicitly optimized to gain interpretability. And on the right side, we have the interpretable by design approaches. So interpretable by design means that the learning algorithm is really explicitly optimized to gain interpretability. Okay. All right, so here we see some examples. On the left side, you see an example for interpretability by nature. Thereby you can see a simple decision tree with a depth of 3. The notes illustrate which feature is considered, or more precisely, which decision is made to split the data set into branches. The tree first splits all instances at petal width 2.45, whereas the next split is at petal width 1.75. So, and the two last splits are either at petal length 4.95 or at petal length 4.85. So those are examples that clearly illustrate that a decision tree with a depth of 3 is interpretable, as you can see. And on the right side, we see an approach for interpretable by design. Thereby, we use the Bayesian rule list algorithm that constructs an interpretable and concise list that tries to explain the entire model. Okay, now I will hand over to Marco.
Yes, thank you. Let's go to the third type of gaining explainability. This one is called the global surrogate approach. The key idea is to use the black box as usually done, but then in turn provide an additional model, which is called a surrogate, which is then used to explain the predictions of a black box model. And this surrogate is global, which means it tries to simulate the whole black box model. One common approach that can be done is to fit a decision tree to a neural network. So in this situation, we consider a deep neural network and a surrogate, which is a decision tree, but it can be done similarly with a rule list, as we have seen before. And in this case, we consider a classification task, even though it can be generalized also for a regression task. The naive approach would be that we consider the outputs of a neural network as Lagrangians. So the network acts like an oracle. So it is providing us the data. We use the output of the network as the labels. And then based on these new labels, we fit a decision tree and hope that the decision tree is simulating the predictions of the neural network. It turns out that this naive approach, even though it sounds like a good idea, is rather bad because, as we all know, decision trees have a quite limited representational power. We will get a low fidelity. That means that the predictions of the decision tree and of the neural networks often do not agree, but also we get a low accuracy, which means that the prediction of the decision tree are also not fitting well to the data. But even though the idea is quite nice, and we were thinking about how could this approach be improved, and the idea was to modify a bit the training of the neural network in a way that we use regularization. I guess everybody of us knows how basically regularization works. We have the classical optimization problem, like a classification loss, and then we incorporate an additional term, which is called the regularizer. Usually, regularization is used, for instance, to get a sparse neural network or to avoid overfitting. In this case, even though we know that regularization is not completely new, we have a different target to our mind. Here, the target is to improve the fitting of the surrogate model to the neural network. This idea is not completely new as well. The first approach in this direction was proposed by Wu et al. In 2018, which is called tree regularizer. The idea works basically like this. We have our classical neural network training, and we would like to fit a decision tree. So we use a regularizer that is aiming to get at an output a rather short decision tree. As we have seen, the shorter the decision tree, the easier it can be interpreted by humans, but at the same time, it should be fit quite well to the neural network. The problem is that this regularization term is usually not differentiable. So these guys in their paper did then the following. They used an additional neural network to estimate the complexity of the decision tree, and this output of this additional neural network is then used to provide the regularization. It sounds complicated. It is actually complicated. We tried it out, and it is quite difficult to use. It's also computationally quite expensive because you have the models that somehow interact. So it's really demanding. So what we came up is with a new regularizer, which we called the sparsity orthogonality regularizer. The idea is to get first a sparse neural network. This, I guess we know what this means, that most of the weights of the neural network get 0. And at the same time, we force that the weight vectors of each neuron are pairwise orthogonal. The idea there behind is as follows. If we do get a sparse, maximally sparse inputs to neurons, it turns out that the decision boundaries of the neural networks get axis aligned, and with the orthogonality, we also ensure that we do not miss some important features. In doing so, we force the neural network to build decision boundaries which can be easily approximated by a decision tree, as we know that the decision boundaries of a decision tree are also axis aligned, as we can see here in the images. The details you can find in the paper here, which is highlighted below. I will show you in a short demonstration how this approach works. We built a demonstrator to show this. On the left, you see a neural network which is trained for doing a classification on steel plates. We would like to discriminate different kind of damages on the steel plate. So I now start training the neural networks. On the right, you can see the training curves. This is done really in real time. This is no, let's say, simulation or video. This is just running on the cloud. Then, of course, what you can do is to try to investigate the neural network, but we can already see this is rather complicated. The numbers we will get at the individual neurons are just numbers. We cannot interpret them. So what we now do is to train a decision tree that tries to simulate the behavior of the neural network. And this is the result. You can see this decision tree is rather simple. It's really short, so it can be easily understood by a human. And it can be easily also investigated, which is then done here in a later step. So for instance, what we can do is to generate some global explanations like decision rules, which is just a path from the tree of the node, the root of the tree to a node of the tree, which gives one of these rules. We can also get feature importance, as Nadia already has shown. We can also get 2D plots of the decision boundaries. And we could also get some local explanations. Therefore, I need to mark some of these leaves of the node. For instance, this particular node here is predicting in 98% of one of the specific class of a damage. We can also get the relevance of a node. For instance, this node here is quite unimportant. It is just covering 6% of all the data, while in turn, for instance, let's see, this one here, the upper node, is covering 52% of all the data instances. So this one is a quite important decision. So here, with this help of this decision tree, we get some insights about the decision making of the neural network. So let's switch
So Marco, can I pause for a second?
Yes.
Just to kind of understand it better. Would you be able to like translate what those actual buckets are?
This one here?
Yeah.
So these are, unfortunately, it's in German.
Sure, no worries. It's not unfortunate. It's just want to understand.
Yeah. This one is just means a bump in the plate. And this is the orange one means a scratch in the plate. So we are just discriminating two different kind of damages that can be observed on a steel plate.
Okay, got it. And the menu options on the right side.
So this upper one here, I close this. This means global explanations. So these hold for the entire model. They are globally valid, like decision rules, feature importance. So this is the feature importance, which says, for instance, the feature X minimum is the most important feature of our data set. The next one is the thickness of the steel plate. And this is some surface feature of the steel plate.
Okay.
And this one here is plotting the decision boundary for the most important features. So on the x-axis, we have the feature X minimum, which was the most important one. And on the y-axis, this is the second most important feature, which is the thickness of the steel plate. And we can see on a very tiny space of the input data, we decide towards a scratch, while for the majority of the data domain, we decide for a bump. And this one are local explanations. They hold just individually for the nodes of decision tree. So they are not globally valid. They are valid for a very particular decision. Okay.
Thank you. Thank you. I appreciate that.
All right. Good. So let's come to the fourth class or fourth type of explanation, which is an instant explanation. Now we leave the global explanations and go towards a data-specific explanation. Here's a relatively large table of the various kinds of instance-based explanations we can find. I just pick one of the most famous examples, which is usually used for deep neural networks, used for image classification or image processing tasks. These are called usually heat map approaches or feature attribution methods. The idea is quite as follows. You would like to highlight which part of the input image is used for a particular classification or regression. So in this case, we would like to see why this neural network is classifying a particular task to one of the given brands, like is it a BMW, is it a Tesla, or is it a Volkswagen? There are various approaches. In this case, we use GradCam, which is one of the most famous ones using to calculate this kind of heat maps. And if the color turns toward red, this is indicating that this part of the image is supporting the prediction of the neural network. Funny here is, for instance, in case of the Tesla, you can see two important parts of the image. First one is here in the front wheel area, but also on the background, you can see the Tesla logo. And also this seems to be an important part of the image to support the decision towards a Tesla. Now you can decide if this is a good prediction or not. So should the network use this background information to make a prediction towards a Tesla, or should it not do it like this? So this heat map allows you to see which part of the image are in the view of the neural network, important for a specific decision. For the fifth type, we look at local surrogates, which is very similar to the global surrogate, but this surrogate only holds for a particular data instance. This class is not that big as the one we have seen before, but it contains one of the most famous explanation approaches, which is LIME, which I would like to introduce, if you do not already know it, in this slide here. So LIME was proposed 5 years roughly ago. It's relatively simple. It works like this. For instance, consider we have this data instance we would like to make a prediction for, which is marked here with the red cross. Then LIME is doing the following. It is sampling randomly data from the input space, and then is feeding this sample data to the machine learning model to get a prediction like red crosses and blue dots. Then in the next step, it is calculating the distance between the test instance, so our initial data instance, and all the sample data. And the closer the data, so the sample data to our test instance, the more weight it gets. And based on this weighted sample, it is then calculating, for instance, a linear classifier, a linear decision boundary, which is, of course, just valid locally for this particular training instance. And as we all know, linear models are well understood, so they can be considered as a white box model. And they help to support or to explain the decision by the more complicated black box model for this very particular red data instance. So this is roughly how LIME works. We have used LIME, for instance, to make explanations on the classification of ship trajectories. So here we have gained a lot of data. In total, it was more than 2 billion data points from a coast area where we would like to discriminate 5 different kinds of ships, like cargo ships, fishing ships, or pleasure crafts. And the idea is to use also the whole trajectory information of the ship to make a classification. This is let's say, the explanation tool we developed to support the operator of such a, let's say, like, for instance, a Coast Guard. In this particular example, you can see on the left-hand side the trajectory of the ship. Here you can see the classification of the algorithm. In this case, the classification is supporting a cargo ship, and then we used LIME to see which kind of input features are supporting this kind of decision. And this is also highlighted on the left-hand side with the color coding, which is can be read as the following. The red part of the trajectory is against a classification of the cargo of a cargo tanker, while the green parts are in favor of a cargo tanker. So we can see that the beginning and the end of the trajectory are very important to get a classification towards a cargo tanker in this case. Now I would like to hand over.
Can I ask you a question here? Sorry,
yes.
Can I ask you a question here, Martin? So the tool.
Yes, sure.
So here, the models, do you have benchmarked with a set of models, or can you upload your own model?
Maybe I can hand over Nadia this question because she was working actually on this.
Yes. Yeah. No. So those are just some specific models. You cannot just upload any models. You have like 5 models we uploaded over there, but it's not designed like this that you can train the model on purpose. Okay,
got it. Thank you. And how about the data sets? It's also a standard set of data sets you tried out with?
Actually, it's the IES data set. It's a ship trajectory data set, and everyone can download it.
Okay. I mean, like, can I switch the data set to a different data set and use the standard classification models?
Yes, you can do.
Okay. So it's primarily just inference, right? So you're kind of inferring. Yeah. Okay. And then the sampling, the background sampling, and the missing data imputation. So those are some of the pre-processing steps you're kind of just doing to. So and it's uniformly sampling, or can you make it like class-based samples, or can you look for specific kinds of things?
Yeah, you can look for specific kind of things, so it doesn't matter.
Doesn't matter. Okay.
Mhm.
Thank you.
All right. Okay, so let us have a look at the open challenges. We discussed a few in the paper, but there are definitely many more to tackle in the future. So first of all, we need a clear definition of explainability and also interpretability. This is really important, for example, for legal issues. In Europe, we have the General Data Protection Regulation, and this really demands a clear definition of explainability. Also, we really need to rethink the problem in the first place. Do we always need to train a black box, or can it just be a simple model? If we can tackle the problem with an interpretable model, there's no actually need to use a black box. Cynthia Rudin described this topic pretty good in her paper, Stop Explaining Black Box Models for High Stakes Decisions. Another important point is the measurement of explainability. We definitely need measures to be able to compare different explanation approaches among each other. Also, much work should be done in the field of combining explanations with ontologies. I think this is a really promising approach that should be tackled in the future. All right. Yes, so let me sum it up. Let's have a look at the key facts. So AI is becoming an increasing part, or already is an increasing part in our daily lives, and the trust in AI is of paramount importance, especially in critical domains like e.g. self-driving cars. We gave an overview of 5 different Xi types, which lead to different explanations. So first we had the model explanations that can be directly inferred from the black box to create a global explainability. Then we introduced the interpretable by nature and interpretable by design approaches. So there you directly design an interpretable model and you don't need a surrogate. Then we have the instance explanations that uses a black box prediction to directly infer an explanation. Then we have the global surrogates, where we train an interpretable surrogate to create global explainability. And last but not least, we have the local surrogates. Thereby you train interpretable surrogate to create a local explainability. Yes, so that's it, and thank you very much.
Thank you.
Thanks for the amazing talk, Marco and Nadia. This was amazing. I kind of got now a structured view of like how have you been like looking at the world and how have you been looking at different kinds of models. I was particularly impressed with the demos. I really appreciate you putting the time and making those demos. Now, are those demos in the open source realm, or is it proprietary, or is that something we could try out?
So in the one I have shown you with a decision tree surrogate, this is proprietary, but we will come up soon with at least an API that can be used so that you can, for instance, upload a black box model and get an explanation in return.
Yeah, and also the ship trajectory classification is currently not available online, but we will work in the future for an example demo.
Okay, cool. Thank you. I think there are a couple of questions. So people in the audience, if you have questions for Marco and Nadia, please type it either in the chat window or in the Q&A window. There are a couple of comments and questions. I'll try to go over them. So I think Mikio had some thoughts in terms of the actual definition of explainability versus interpretability. I know it's a confusing topic for many. Would you mind just kind of just summarizing? I know you've spent a lot of time on it. How do you kind of tell someone who is in the practitioner space on working with different models, what should they be focused on in terms of whether to explain models or to interpret models? And if the audience is going to be end users, how should they approach the problem versus if they are trying to do model validation on their own, how should they address the problem of interpretability versus explainability?
Nadia, do you start?
Yes, I can start. So let me sum it up. So I think most of the people are asking, what is explainability? What is interpretability? What's the difference? It's currently very used synonymously, but I think that explainability refers more to post hoc approaches. That is where you try to train a surrogate or directly infer an explanation. And on the other hand, you have the interpretability that is really linked just to the interpretable models. So where you directly really can see what has the model learned, what's the output. So this for me is the difference between both of them.
Okay.
Maybe I would like to add something. What is also often used in is then the word of transparency, like use a transparent model. But usually I would like to see transparency is a more, let's say, general topic. It is also about, it's not only maybe about to provide some explanation, it's also to be transparent what kind of models are actually used, what is the data looking like, how was the training done. So also provide all the meta information that is necessary to understand the machine learning solution as a whole. So it's not only concerned about explanation of a particular prediction, but the whole, let's say, machine learning pipeline.
Okay, cool. I think, Mickey, you added a couple of comments in there just to add to that. So, especially when there is no inductive and declarative formulation in the architecture of the model we are using. The second question I would like to just bring up is like, what are the main approaches to combine explainable AI and ontologies? Do you have any thoughts there?
Yes, so currently there are some approaches that already use the topic of ontologies and explanations. So, for example, you can just take a decision tree to explain the decision process of a neural network, and thereby you can combine the structure of the ontology really to structure how the neural network is built up with ontologies. We also list some approaches in our paper. For example, tree-pan reloaded is such an approach you can directly use.
Okay, cool. And I think there was another question. How do you think human involvement should be used to evaluate explainable AI performance? Question on evaluation. Yeah,
that's a good question. As Nadia pointed out, this is actually, so how to evaluate in general, the value of an explanation is an open topic. There are not the measures that can be used how good an explanation is or not. There are some, let's say, surrogate measures, like the depth of the decision tree. The longer or the deeper decision tree, the more intransparent or opaque the model is. But this is just, as I said, a surrogate measure. And I think, and this is what we also did with some of our studies, it is in fact necessary to involve to some degree also the humans, because they are consuming the explanations, and because explainability is a rather subjective topic. It depends a bit on who is actually the consumer. Is it a machine learning engineer that would like to improve his machine or her machine learning pipeline, or is it a decision maker who has no clue about machine learning, but who has to do some decision based on the outcome of a machine learning model? And depending on this, let's say, consumer of the explanations, you need their involvement to see whether he can or she can work with explanation or not.
Cool, thank you. And I had a couple of questions, just my professional interest and also some of the research I had been doing. In terms of the whole notion of explainability. So when a couple of years back when I was teaching machine learning, we would stop at like, okay, here is the model, here are the results, deploy it and go figure kind of a thing. So now everybody is talking about explainability. This year, as we were saying, the interest is exploding. Everybody wants to understand explainability so that they can explain models. Now, when it comes down to pragmatic use of machine learning models in the enterprise, one of the challenges is that machine learning itself is complex, right? So, you have deep neural networks, you have ensemble models, you have different methodologies, hyperparameter tuning, computational aspects of it, data processing, augmentation. All this is a pretty complex process, and you both are researchers working in with a network of researchers wherein you can bounce ideas, you can experiment, you can try and do various things. But when you think about like enterprises, they're working at an API level, or probably they are working at a rudimentary understanding of what happens behind the hood and under the hood, and then they are focused more on the use cases and applications, right? But the whole notion of understanding these additional layer of metrics, an additional layer of complexity of understanding explanation before they can actually explain models. Do you think we'll get to a point wherein the industry is going to adopt explainability with the same level of interest as the researchers and many of the vendors are actually building?
I think yes, it is going towards the direction. At least here in Germany, we observe this. You have seen that the European Union was defining a strategy on an AI, which is putting a spotlight on trustworthiness, which is maybe a bit different from, let's say, the strategy you can see in the US or the strategy you can see in China. So this is often called the third way of AI. This is how the people in the EU is calling it. So trustworthy AI as a difference to the other strategies. And we see that many companies and professionals are adopting. For instance, in my case, I'm working a lot with manufacturers. So and in manufacturing, you use, for instance, deep neural networks to do quality control. You get an image of your workpiece, and you do an automated quality inspection. And then the people just do not accept whether the algorithm is saying it's okay or it's not okay. They often ask, why did you do this certain predictions? They really would like to understand, because then they can see what is actually wrong with the manufacturing process, and this would then allow to optimize. So for instance, they use this kind of explanations to get a deeper insight about what is wrong with the manufacturing process. Similarly, we observe it, for instance, this is also increasing in the automotive industry, where the regulations are more strict. Like if you go towards autonomous driving, that they would like to, they use a lot of machine learning to make all this data processing, and they would like to use in their software development suites also explanation approaches to support them in building machine learning models. We just recently started a research project where some of the automotive companies are involved, where it is actually going towards this direction, to come up with a software suite that is not just doing building machine learning models, but also providing explanations to see already in the development stage if the model is doing as it was intended for.
Yeah, I guess like I completely agree. I guess my question specifically is about interpreting interpretations, right? So the skill level required to interpret is pretty high, and to bring it in context to the applicable problem is also requiring a very high level of skill, not only in the machine learning space, but also in the domain space, right? So I've been having multiple discussions over the last weeks, on like what does it actually mean for the industry, right? Because on one end, you can think about like hiring a lot more experts to basically support the adoption of AI within the enterprise, and that's why we are working with organizations like Premier to put together courses in algorithmic auditing, wherein you may have to bring in third-party experts to periodically look at models or to evaluate the sophistication of your interpretation, because many a times you go to the simplistic tool-based approaches just to meet a particular standard, especially when there is regulation, right? So you do the bare minimum required, because if it's regulated, then say, okay, fine, let's just do this because someone else is asking us to do it. But the risk which goes into the models, the risk of you not understanding what you're deploying is there, right?
Mm-hmm.
And especially with systemic applications, with applications which are not just restricted to your own domain, but there may be like societal implications, there might be implications beyond the actual just usage of a model, right? So that's where I'm kind of thinking, where will the direction go? Wherein is it going to be tooling, wherein you have extra layers of abstraction, wherein APIs or things wherein you could provide dashboards, wherein you could understand what's happening, or it would be like someone was asking, like bringing in human involvement, wherein you would say, you know what, we'll bring these tools to humans so that you don't have to start from scratch, but you bring in the required expertise from outside so that you can understand what's actually happening, or maybe even train internal folks to say, this is like out of all the other methodologies, like the 5 methodologies you proposed, right? So, which one is contextual for us? Which one is sufficient? Which one is actually something we are doing more than what's actually required? And also gear up towards the challenges because these are data-driven problems. When we don't have the data, what do we do? When we are kind of looking at imbalanced classes, what do we do? All those questions which come up in the research world, how do you kind of make sure that people do understand? So that's where I was kind of thinking, like, the research is kind of moving much faster than our adoption of these tooling in the industry. So how do we bridge that gap?
Yeah, okay, I see. It's not easy. It depends a bit. For instance, maybe, and this is just a part of the answer, that we see that the big enterprises, I think they have no pain also to hire experts that allow them to incorporate the necessary level of explanations they need for their business. If you have, let's say, like for example, the big car brands we have in Germany, for instance, or companies like Bosch with several thousand of employees, then they can afford this effort. They have the dedicated AI teams, and in many cases we know that they are also working on this explainability stuff because they need it for their products. The picture is a bit different if you look at the small and medium-sized enterprises. They often do not even have, let's say, the budget to afford a single data scientist. And here I think it is a good idea to get third-party support if the company is intended to use machine learning models and it is working in a regulated environment, that they hire or get support by a third-party company that is supporting them in gaining the desired level of explainability. This is what we observe here. So like in the part in Germany we are, the majority of the companies are SMEs. They are quite, let's say, powerful in their niche, but they are just in their niche. They do not have a 10-person team of data scientists that is building machine learning solutions, not even thinking about explainability. So they then involve third-party companies to support them in these efforts.
Perfect. Thank you so much. And it's 1 p.m. East Coast time, and it's already night for you. I really appreciate you taking the time and joining us. And the beauty of online sessions is it doesn't matter whether you're in Germany or in Boston. We can all get together, have a good discussion. So this was an absolute pleasure to have you, Marco and Nadia. This is something, a topic which is near and dear to our heart. And I'd love to continue the conversation offline to see how we can bring amazing tooling you're building and get it to the hands of the users, because that's where the is, so that they can build in their models and extend the research and usage of these amazing technologies. Thank you so much. And for people who are going to be joining us in the next few sessions, next week we'll have Dr. Daniel Duffy and John Mark talking about various aspects of Hilbert spaces and machine learning models. And please do join us next week. And please go to winterschool.splashtip.com. I'm just going to share the link with you. And give me 1 second. It's so this is next week's session. It's Q Speaker Series 24.splashtip.com. But if you go to q.academy, you will have all the details to sign up for. So thanks again for joining us in today's session. And we will continue the discussion online. And thanks again, Marco and Nadia. Have a good night. Take care.
Thank you.
Thank you.
Bye.